All right, here's our recording for Wednesday. It comes from chapter 16, and it addresses two different theories of geology. It talks about conventional geology and tells the full story, and then talks about short age geology, telling the full story of Earth's history. More time is given to short age geology, which ought to make sense because conventional geology, I think the story is more familiar, maybe not necessarily to us, but to most. And so, more time is given to short age geology, telling that full story. And as you prepare for our class on Wednesday, what I want you to do is to prepare to talk through some of the finer points on here. As I put these slides together, there were so many things we could have talked about. Relatively long chapter, and so what I did was try to highlight the major overarching story, and then we can talk about some of the finer points in class on Wednesday. So the story begins with Precambrian deposits, and inside of these Precambrian deposits, we have evidence of geological processes. There are evidence of craters, meteorite strikes, even craters with weathering around the edge, erosion around the edge of these craters, creating irregular craters, and craters with other craters inside of them. Not only that, but there's evidence of sedimentary processes. There's evidence of folding and erosion and other geological activities. So there's a lot of evidence in Precambrian deposits of geological processes. And so, considering that many flood models begin at the Paleozoic, which is the beginning of the Cambrian, you have to tell this story of what's going on there, although it's a little bit more difficult to do so. Also in these Precambrian deposits, we have evidence of living forms, especially a number of single-celled forms. Here's a fossilized stromatolite, a structure made by bacteria pulling minerals out of the water and then cementing them into these structures. We can find living stromatolites in Australia and in some other places, and they look very similar to fossil stromatolites. And so we have a large amount of evidence of living forms in Precambrian deposits as well. And again, we've got to tell that as part of the story. So again, focusing primarily on short age geology, there's a question that comes up, well, what was it like immediately following creation? And so some proposals that the authors made was that the crust may have been more complex than it is now. They talk about that the present Earth does not look incredibly well designed at the crust level. You have areas like deserts and places where you don't get enough moisture to sustain a rich assemblage of life forms. And they say from looking at the abundant living forms here early in the fossil record, especially in the Cambrian explosion, in the Cambrian where we have our highest diversity at the phylum level, that they argue that maybe the crust was just as complex as living forms, creating a number of environments that no longer exist and sustaining life forms that could not exist following the curse. And so what happened? So if we have this wonderful creation in which even the crust is incredibly well designed to sustain high levels of biodiversity, well, what happened? Well, we know the story that Scripture tells is not immediately, but pretty soon after creation, man rebels against God, usurps God's authority to place his own authority, and with that comes a curse. The breaking of what you see as shalom, this peace, and you instead you get chaos, and the entire earth starts to deteriorate, starts to feel that weight, and then God destroys the earth. God destroys the earth and all terrestrial air-breathing forms except for those taken onto the ark, including humans. And God essentially get starts a new creation left over as a remnant. So what happened is we have this deterioration, which is going to start to mar God's creation, and it does. And then we have a new creation. And so what we have now is not like what God designed, and presents challenges for us to be able to tell this full story other than with what Scripture tells us about this story. So what do we need to know about plates in order to fully understand the rest of this story? Well, the main thing here is you have to remember, we've talked about this before, I believe, that continental plates are made primarily of granite, granitic crust, and have a specific gravity of 2.7, so heavier than water. But if you look at the basaltic crust here that underlies the oceanic or the oceans and forms our oceanic plates, these have a higher specific gravity. So these are heavier than water, but they are lighter than the basaltic rock, and therefore float on top of basaltic rock. And so the reason why the continents are not the basin where everything runs like the oceans are is because the rock forming those continental plates is less dense than the rock forming the oceanic plates. And so that's why our basins, our main basins globally are in the oceans, where we actually get the lowest amount of sinking into the underlying mantle. So what deposits are flood deposits? So we have some different flood models that talk about the entire geological column, and then so we need to start, figuring out what are flood deposits. This is probably the most common. This is the view of the authors of the textbook. Most or all of the Paleozoic, Mesozoic, and the very earliest Cenozoic are flood deposits. And so the flood probably begins at the Cambrian explosion, accounting for why do we have a burial of a rich variety of different forms. Another idea is some of the Paleozoic formed in the oceans before the flood began. So the idea here is maybe the earliest part of the Paleozoic formed in the oceans, accounting for why those are marine deposits, and but still then not providing a rich amount of evidence of where those different forms came from. Although if they were all separate creations, then you don't need to account for where they came from, because Scripture actually gives you that account. Some flood models actually still start at the beginning of the Paleozoic, but take the flood boundary all the way up until either the beginning of the Pleistocene or part of the way through the Pleistocene. And so other ideas are that the flood formed a very minor part of the Phanerozoic, which is the Paleozoic, Mesozoic, and Cenozoic all together. And then there are, various other flood deposit ideas. The one that we're going to work with is this up here, that most or all of the Paleozoic, Mesozoic, and earliest Cenozoic are flood deposits. So how do we know that the continents were covered by water? Because that's an integral part of both stories, the conventional geology story as well as short age geology story. Well, first off, Scripture tells us in Genesis 7 that the earth was covered with water. It says the waters prevailed above the mountains, covering them 15 cubits deep. And the authors of the textbook talk a great deal about this. Like, how is this even possible? There doesn't seem to be enough water on earth to make this possible. And they talk about that it seems as though the continental plates before the flood are being severely destroyed and the mountains lowered by erosion during the early flood. And so this is something that if you could lower, well, if the pre-flood world, first of all, didn't have as much elevation differences than we have now, you could account for this as well. But if you destroy a lot of those high elevation areas, you could accomplish this as sediment is distributed more evenly across the globe. They also talk about the possibility that the continental plates prior to the flood no longer exist, that those continental plates were subducted back into the mantle. And so if that happens during the early flood, and they say that may have been the first event to begin it, the shifting and the subducting of these continental plates, then you may not have had much land to cover anyways. Also, we know that the continents are covered by water, not just from the Genesis account, but the fact that we have fossils, especially marine fossils, buried on our present continents. We know that our present continents were underwater because they had to be the lowest point in order for that sediment to accumulate there, and they had to be underwater in order to provide the environment necessary for burying these huge amounts of material. So then we have questions, well, where are, if you're going to take a bunch of marine material and you're going to bury it on land, don't you think you would bury it with some of the plants that were there? And so from a short age geology perspective, there should have been plants on that land that got buried underneath these marine deposits. And so where are those plants? From a conventional geology perspective, they didn't exist yet. But again, this is where one of the ideas, well, maybe the pre-flood continental plates subducted, and so they disappeared. And so here's the idea of subduction. Here we have, in this case, an oceanic plate actually undercutting, getting underneath the continental plate because it is higher density, and then once it gets back into the mantle, it melts. And the authors of the textbook talk about there being evidence of huge pieces of rock in the mantle that are 3,000 degrees Celsius cooler than the mantle, indicating a relatively recent burial of massive pieces of rock. And so is this subduction of oceanic plates, or is it subduction of what used to be continental plates? And then so we have this question, well, how is this possible? Because continental plates don't subduct underneath oceanic plates, because again, they're lighter. And so a hypothesis that the authors present is, well, maybe the original continents were made of basalt, like the oceanic plates were, but it was made up of a type of vesicular basalt, so that you have, in this case, this is pumice, probably, they talk about this being an extreme example, where you actually have pockets in this where you could fill it with air or with water to lighten the material, reduce the density, and allow it to float on top of these other basalt plates. But when that water pours out or the air leaves, now it's equal in density to the oceanic plates and is more apt to actually subduct. So where did the organisms come from? So if we have these, our present continents, if they weren't the original continents prior to the flood, then you can't be looking at the burial of where these organisms live, but instead you're looking at the evidence of where these organisms got buried. And so then the question is, well, where did these organisms come from? And what's interesting is in these deposits, almost the entire Phanerozoic, again, Paleozoic, Mesozoic, Cenozoic, especially Paleozoic and Mesozoic, there's an enormous amount of evidence of paleocurrents. You can see some of those here in this rock, where you can see that as these rocks were forming, there was moving water. And so if you have, strong enough currents, you could carry these organisms from a really far distance. And so there are some challenges to this idea. The authors actually present some of those challenges. How could you carry those organisms over a long distance and allow some of them to survive long enough to even leave tracks? Because we have tracks that form in these rocks as organisms are being buried. Basically throughout, and so we do have some challenges, but you can't ignore the evidence of incredible water movement and an illustration of these paleocurrents that look like they're bringing these materials being fossilized from somewhere else. So how did the deposits change through time? And so this is part of the story of short age geology. Well, you see in Paleozoic and Mesozoic deposits, these flood basins, these tend to be more regional, massive burial basins. But when you transition into the Cenozoic, it becomes far more local, and part of what allows that to happen is mountain formation. And so here we have a process called overthrusting, which can function to actually build mountains. Here you have the Canadian Rockies, built in part by this overthrusting. And so the authors of the textbook talk about, well, this process is actually easier to accomplish when you have these sediments underwater, which actually supports the formation of these mountains when they form, regardless of what your view of origins and the Earth construction is. But basically, we have these really high elevation points that now start to limit the ability of water to move long distances, and you get these valleys in between peaks that now become your basins for sedimentation. We also see the deposits and the processes becoming less catastrophic as you move through the fossil record. You can see that in terms of fewer, mass burials on a global scale. But you also see it in terms of less extreme formation. So the idea here is that the Grand Canyon was carved very shortly after the global flood, and we don't have anything on that scale made more recently. So the Earth becomes less catastrophic as you move through the fossil record as well. Animal fossils change through time. We've talked about this many times, that you get basically a story of increased complexity as you move through the fossil record. And here is basically a representation of how this might have happened, not representing a transition through time, but rather representing a transition through space. And so here is a representation of different biomes or ecological zones and their relative location. So what you're looking at in these flood deposits aren't a transition through time, but rather a transition through different biomes laid down during a flood. And the authors of the textbook actually talk a great deal about, even in the midst of chaos, chaotic flooding events, that the sedimentary processes tend to be very predictable and very orderly. And so, on a global scale, you would probably expect the same thing, that even in the midst of chaotic events, that your sedimentation or your sedimentary processes are very ordered. Animal distributions also change. Here you have a artist representation of old world monkeys rafting over to the new world. And the authors of the textbook even talk about that biogeography used to be entirely described as vicariance, where basically some geographic barrier separates groups, and that's the only way to explain animal distributions. And so if you've got old world monkeys and new world monkeys, old world monkeys in Africa, new world monkeys in South America, they must have once have been original single distribution that then, as those continents split apart, they were split apart. But a lot of these stories of vicariance don't fit the account that we have, where the continents split before there are any fossils of those organisms. And so now, in the last 20 years or so, we've started to explain a lot more of these distributions through dispersal, and a lot of this through rafting. But how do distributions change? In Paleozoic and Mesozoic deposits, animal distributions are a little bit more, not chaotic, but maybe less predictable. But once you get into Cenozoic deposits, you basically find fossils living in the same area where their close relatives live now. And so animal distributions change a great deal. So then we have a question with the short age geology that we have to account for, and we have to describe, is where are all the higher life forms? And so here's a diagram drawn by the authors of the textbook, demonstrating the fossil record. Here's universal common descent, the conventional story that the only organisms leaving fossils are those that are around. All organisms that are around are pretty much leaving fossils, although the fossil record is obviously going to be biased towards organisms with a more expansive distribution, higher numbers, and hard body parts. But very different than what we have in a biblical story. Is these organisms are around the whole time, and yet they're not leaving any fossils. And so again, this maybe provides some of the fuel for why the authors of the textbook talked about that, well, maybe the continents that existed before the flood no longer exist now, and so we had these higher life forms living in places where they were not going to be buried. And they talk about an analogy of 5 flood events that happen in your backyard to leave mud deposits, and you end up with dog poop washing into your yard in the 5th storm, but the dog was there the whole time. It was just the flooding event took a different route that time. So here are some Paleozoic prints that look very similar to modern bird prints, but are not interpreted that way because birds are not supposed to have existed then. This is just one example. We have other examples of prints that could be interpreted as mammal or bird prints, but are not, because from the conventional story they should not have existed then. Where are higher life forms? What's interesting is the authors of the textbook actually talk a great deal about the Southern California area, and during the Pleistocene, actually containing a number of megafauna, mastodons, mammoths, American lions, large camels, the Jeffersonian sloth, just a massive sloth. And so we have just a great number of these buried in these tar pits in La Brea. And then we have this question, well, it doesn't seem to be difficult to bury these things. Why don't they show up until the Cenozoic? And again, there are some challenges, and could be explained by is they lived in an area that was not conducive to having the organisms that died there end up where they got buried. And here's a representation of Mummy Cave. The authors of the textbook talk about this, where you have basically layer after layer after layer of Native Americans being buried in this area and then continuing to use it. And you can actually see the transition through time in the technology. So we're indicating definitely a trajectory through time. And again, an issue where it's not all that difficult to find evidence of human activity. Why don't we find it basically before the Pleistocene? And so this is one of the things that I think drives some to propose that flood deposits actually go up until part of the way through the Pleistocene, to help account for why we don't have any human fossils. And the last thing we need to talk about during this lecture before we actually get together on Wednesdays, how much post-flood evolution happened within these created kinds. And so the authors of the textbook talk about the horse series and how it, one, is a what you might expect as you get diversification in a created kind after the flood, that you move from smaller and more generalized to larger and more specialized, and is very similar to what you find in a number of mammal groups and bird groups following, in Cenozoic deposits, the move from smaller and more generalized to larger and more specialized. Some of them don't follow quite that same rule. We've got the whale series that we've talked about many times, and here I think the strongest evidence right now seems to indicate that we have at least 2, if not more, different creative kinds of whales and terrestrial forms with some whale characteristics. And so the jury's still out on this. For me and for a number of creation biologists, trying to figure out exactly what is this telling. But other than that, I mean, the horse series and a number of these other groups of mammals and birds do seem like we're getting a significant amount of diversification following the flood, which is really exactly what you would expect to happen if you do destroy all terrestrial air-breathing forms other than those that were taken onto the ark. A lot of open environments, a lot of open niches, providing opportunity for rapid diversification.